Now, from this slide here, we will be looking into each examples, okay, in this particular chapter. So the first one, you have this question here. It's an easy question. Okay, a mild steel bar of 25 millimeter in diameter has an allowable stress of 138 Newton per millimeter square in tension. So the units given here is in Newton over mm square, and then the diameter is in millimeter. Remember that if you were to convert any of these to meter, make sure the stress also you have to convert it to meter square. Now in tension, and if the bar is to be used to resist tensile force, what is the load that can be applied? So here what we have is tensile force or tensile stress. So the area that you consider, remember, first thing is it must be 90 degree. So this is the force. The area that you consider should be the cross-sectional area, which is perpendicular to the force, the line of action of the force. So the area for this example, because they have stated here is diameter, so that means it's a circular cross-section. So the area, the cross-sectional area that we can use is either pi r squared or pi d squared over 4. So first thing is you need to find out the area. Okay, so the cross-sectional area, because in order to find the tensile stress, you need to have the force, okay, and the cross-sectional area. But in this case, you don't have the force or the load. So the question has asked us to find the force. So first thing is you have to find out the cross-sectional area. So the cross-sectional area, either you use pi d squared over 4 or pi r squared. D refers to the diameter of the cross-section, that is 25 mm. If you are referring to the radius, it should be 12.5 mm. So if you were to consider mm squared, that means you have to consider, or you have to remain the diameter as in mm, or the radius is in mm. Because since they have given us the stress in Newton per millimeter square, so it is better for us to calculate the area in terms of mm. Okay. So I have put down a note here, okay, in red. Remember, when you consider the area for any direct stress, the area must be perpendicular to the direction of the force. The note here. So the cross-sectional area 190.87 millimeter square. So the force, based on the formula that is given here, tensile stress equals to force over area, force over cross-sectional area. So if you want to find the force, it will be the stress multiplied by the cross-sectional area. So you have 138, which is in Newton per millimeter square, multiplied by 490.87, which we have calculated, in mm square. So the mm square will cancel out. So you have the force, which is in Newton. So you have 67740 newtons. So 67,740 newtons. So that is equivalent to 67.7 kilonewton. So if you were to find kg from this, then you must multiply or divide by 9.8 or divided by 10 meter per second square, up to you. So that is for the first example. Now the second example, a square mass concrete column, with a mass of with dimensions of 600 mm side and 2,500 mm of height, carries an axial load of 600,000 kg. That means the load, okay, of the beam is 600,000 kg. Carry a load of 600,000 kg. Sorry. Now, if the concrete density, now here in this question, they has given us the density of the concrete material, 2,200 kg per meter cube. Why they have given us the density? So, the moment when you see questions like this, when they have given us the density, usually we have to include the mass or the weight of the concrete column itself, other than the 600,000 kg force that is applied or load that is applied. You have to also include the mass or the weight of the concrete column itself or the beam itself. So therefore, you have to work out two different loads. One is due to the external applied load, and the other one is due to its self-weight. That means the concrete beam or the concrete column self-weight. So here in the diagram, I've shown you that you have 600,000 kg of load acting on the concrete column, and you have its self-weight acting along on its CG, on the CG of the concrete column itself, with a density of the material of 2,200 kg per meter cube. So how to convert 2,200 kg per meter cube to kg is to multiply the 2,200 kg per meter cube density by volume. So if you multiply this by volume, you get a mass of something in kg. So you can add it with the 600,000 kg which is applied, so you can find out how much is the total load that is actually acting on the concrete column. So here I put a note again, okay, to remind you the area that you consider must be 90 degrees to the line of action of the force. So applied load, okay, so it is 600,000 kg multiplied by 10. So I use 10 for the acceleration to gravity or the gravitational pull of 10 kg per meter square. So you take this multiplied by 10, you got this amount of applied load in Newton. Okay, the self-weight of the concrete column. So you have to consider the density. Okay, the density of the material multiplied by the cross-sectional area. The cross-sectional area multiplied by the height, you get what? Cross-sectional area multiplied by the height, you get the volume. So volume times density, you got mass. Mass times gravity, you got Newton. So you have this. So what do you have here? So you got 19,800 Newton. So we add up both these values. So to form a total load of 6019800 Newton. So that is the actual total load that is acting on the concrete column itself. So the stress, okay, is equals to force or load times cross-sectional area. So you have this. So you have the answer of 16.72 mega Newton per meter square. So that is the stress that is developed in a concrete column. Okay. So in this case, remember, you have to include the density of the material itself to calculate the self-weight of the concrete column. So the example, so in this slide here, it has only 3 examples, the others one in other parts. So example 3, a load P, there's a force P here, okay, is applied to a steel rod supported as shown in the diagram, aluminium plate, okay, into which 12 mm diameter hole, this is your 12 mm diameter hole, has been drilled. This is a hole that is drilled onto the aluminium plate. Knowing that the shearing stress must not exceed 180 megapascal. So now they have given us shearing stress. So when you consider shear stress, remember the area must be in the line, that means in the same surface or in the same line as of the line of action of the force. The area that you consider must be parallel or in the line of action of force. Okay, so 180 MPa megapascal for the shear stress, and then 70 megapascal steel rod 180 megapascal shear stress for the steel rod and 70 megapascal for the aluminium plate. And find the largest load P, the force here, that can be applied to the rod. Okay, how much of P can be applied to the rod based on the 2 different stresses. Here I have the working. So first thing is for the steel rod. For the steel rod, the cross-sectional area, the area for the shear, So you have to consider the surface area. So because you are considering the force that is in this direction, so anything that is in the same surface as of the force, the line of action of the force, should be the surface area of pi d. Pi d is actually the circumferential length, of this rod, the steel rod, the circumferential length of the steel rod, multiplied by the thickness. Okay, so this is, sorry, the circumferential is here, the hole, okay, the hole, not the steel rod, the aluminium plate, the hole and the thickness. So the circumferential surface, internal surface of the drill hole, okay, is pi d. So the diameter should be referring to 12 mm and multiplied by the thickness. You know, when you consider the internal circumferential surface, so the circumferential length should be pi d multiplied by thickness. Okay, so you have this area for the steel plate, and then shear stress is equal to force over area. So you just apply the area that you have found and the shear stress that you have got. You can find out a P, a load, the load based on steel plate alone. Then you calculate the next one is based on the steel rod. So the steel rod, you have pi dt as well. So that is the area A2 1.00531 times 10 to the power -3. That is the surface area of the rod. The surface area of the rod. Okay, so that is based on 8 mm. So you have shear stress, which is also force over area. Okay, and now you have to find out the force. So you have the stress multiplied by the area. So you got the force based on the steel rod is 70.372 times 10 to the power -3. So the question asks us to find the largest load P, okay, that can be applied. The largest load that can be applied. So now, you see there are two different loads here. One is 67.8, the other one is 70.3. So if you apply 70.3 for the aluminium plate will fail. Because the aluminium plate can only stand 67.8. The steel rod can stand 70.3. So if you apply 70.3 to the aluminium plate will fail. But if you apply 67.8 to the steel rod will not fail. Because it can withstand a load up to 70.3. So 67.8 Newton is safe for the steel rod, and it is also safe for the aluminium plate. But if you use 70.3 apply for both steel rod and aluminium plate, the aluminium plate will fail under 70.3. So since the question asks us to find the largest load which can be applied to the rod, okay, actually without failure, is the value 67.8. Okay, so that is the end of the slide. Okay, 3 examples here. Okay, sorry, there's one more example. Okay, so in this question here, you have 3 wooden planks. Okay, they are fastened together by a series of bolts to form a column. Now the diameter of each bolt is 12 mm. And the inner diameter of each washer is 16 mm, which is slightly larger than the diameter of the hole in the planks. Find the smallest allowable outer diameter of the washer, knowing that the average normal stress, here you have normal stress, and you have shear stress. You have normal stress and the bearing stress, not the shear stress. You have the normal stress and the bearing stress. On the washer, one is on the washer and the other one is on the bolt. So this is the solution that I've given. So you just take a look at it. Okay, so this part here you have to take a look at your own. Okay, so we continue next lesson or next slide.